Okay, great. Yeah, well, today I'm going to talk a little bit about an issue that you will see in the literature. The title of my talk is Deconvoluting Oil and Gas Condensate Mixtures in the North Sea and the Effect on Identifying Petroleum Systems. Obviously, we need to establish the relationship between the oil and the source rock before we can start doing basin and petroleum system modeling. So this is like a very fundamental thing that we need to do. However, despite some documented pitfalls, I am still seeing many papers that publish problematic oil and oil source rock correlations based on compound ratios determined on dead oil that lacks, of course, the volatiles. Mixtures of petroleum are probably much more common than many of us are aware, and they pose issues. They pose issues for assigning genetic affinity. They pose issues for assigning the proportions of contributing end members, and they pose issues related to predicting physical properties such as gas-oil ratio, or I'll refer to them as gas-liquid ratios. So we know that compound ratios mix in nonlinear fashion for end members like black oil and gas condensate. And in places like the North Sea, this is certainly a process that's occurring right now. We're mixing black oil from for example, Jurassic source rock with gas condensate from deeper, more gas-prone sources. So these correlations and these allocations of end member contributions really apply only to the molecular weight range of the analyzed compounds. That's what this talk is about. And I undertook this work with Andrew Murray. We recently published I presented this at the AAPG meeting, the virtual meeting a few weeks ago, and it's now one of these search and discovery articles. And we also have submitted a paper to APG Bulletin, which is accepted and will be published someday, soon, hopefully. Okay, so you've seen this slide many times already. I'm going to put it up one more time, and I'm putting it up not as a student. Certainly students appreciate the support that you as industrial affiliates are providing, but I think I speak for all of the principals in the program. We also really appreciate your support, and each of you who represent your companies can be proud of your management. You have a forward-looking management that hangs in there and continues to provide support for affiliate programs, even in tough economic times like we're facing right now. So thank you very, very much for your continued support. All right, let's talk about this work that we did. The question is, what is the impact of mixed light and heavy petroleum on fluid source assignment? In other words, what is the petroleum system? What's the relationship between the fluid and the source rock? And what is the impact on predicted gas to liquid ratio? It's very important for a company in exploration to be able to predict for an undrilled accumulation what that gas liquid ratio is going to be. So we approached this in a novel way. We actually took biomarker concentrations. These are ppm concentrations for a series of biomarkers that were easily measured, and we mixed them mathematically in 4 pairs of mixtures, binary mixtures. And these pairs of mixtures had GLRs, gas liquid ratios, ranging from 100 to more than or about 50,000 standard cubic feet per barrel. The cutoff there is about 3,000 standard cubic feet per barrel. Below that, 3,000, we're talking about black oil. And to make it simple, above that, we're going to be talking about gas condensate. And we mixed those mathematically, right, in 5% increments. And then we went ahead with our chemometrics to see if we could assign genetic families and we used hierarchical cluster for that, the standard approach using biomarker ratios. That's the traditional approach that's used. And we also used alternating least squares regression, or ALS, and we did that two ways. We did it with ratios, and that's the way most of these papers I'm talking about do their deconvolutions or their allocations. They use ratios. We also did it with concentrations. So all of these samples, all of the samples that were used for the mathematical mixtures had an internal standard, so we could quantify the ppms of those individual biomarkers. So for the HCA, the hierarchical cluster analysis, I used 17 independent variables here. These are source-related variables. Many of you are familiar with these variables, and we basically used our N members from the GeoMark RFD base. They allowed us access to that, and we went ahead and did our mathematical mixtures, and then we did our hierarchical cluster analysis. So the advantage here, as opposed to doing this in the laboratory, is that there are no issues with error introduced by evaporating gas condensate as you're trying to weigh it, right? So this is done mathematically. So here are the four mixtures. Now I'm going to talk only about two mixtures here because I know many of our affiliates are interested in the North Sea. So here's our first mixture. That's group 2. And we're mixing a gas condensate, right, with a GLR of 12,600 with an oil with a GLR of 1,000. Now this is from the Dropney Formation. And this one up here originates from the Sleipner-Huygens. So Dropney is Upper Jurassic. Sleipner-Huygens is sort of Lower to Middle Jurassic. Black oil mixed with a gas condensate. And this is the ratio of those two GLRs. See the GLR ratios go up. Here for tribe 3 or family 3, we mix these in 5% increments. This is also in the North Sea, a UK North Sea with a Norway North Sea. And these are sort of mixtures you'd expect to see there. We have a high GLR N member with a 20,000 GLR, gassy source. This is from the Pentland Formation. And this oily N member with 1,500 standard cubic feet per barrel, that is also from the Upper Jurassic. That is from the Kimmeridge Clay. So let's talk about those two mathematical mixtures. And what we did first was we used those 17 source-related biomarker ratios in the traditional way, and we created a cluster diagram. So here's a hierarchical cluster diagram that's very informative. You can see we have 4 nice families. The families are these mixtures that we made artificially by mathematically mixing them. And an interesting thing you'll note here is that the ratio between the high and the low GLR, as it increases, the cluster distance decreases. Okay, so we get a tighter group. The bigger the difference between the gas condensate and the oil. So we won't talk about the Perth Basin. Mixing condensate and black oil is a big problem down there as well, but we're going to talk about the North Sea, family 2 here, and family 3. Now I say HCA, hierarchical cluster analysis of these 4 binary petroleum mixtures, is misleading. What do I mean by that? Well, you can see here the cluster distance between these 2 families in the North Sea is not that great. So yes, they're from similar parts of the world, and that we would expect that. But something is a little strange here, because you can see here virtually all of our mixtures are plotting together. And then there is the N member for that mixture, which is the Coley N member, that plots down here separately. It's an outlier. The Coley N member, remember, has a GLR of about, I believe it was 12,600. Yeah, there it is. So what this says is that this mixture, this tight cluster of samples here, if you analyze those using standard HCA, you're going to say these are all looking like Dropney oil. Now, so basically, the the HCA is biased against that gas condensate end member. They all look very similar to dropney oil. And one might look at this and say, well, there are some differences here. They're pretty small, but they might be due to organofacies differences in the source rock. Not so. The truth is we've mixed these in 5% increments. So this is actually very misleading in terms of source. Some of these samples are 90, 95% Coley-Sleipner-Huygens gas condensate. So our hierarchical cluster analysis is misleading. It also applies down here for this one. Okay. So let's look a little more detail. Let's look at the South Viking Graben. This is from a paper by Chris Cornford in 2018. In the South Viking Graben, we have the Dropney Formation, which is an equivalent of the Kimmeridge clay, and it's an oil-prone source rock. It makes primarily oil, has a low GLR. Okay. However, if you look at geochemical logs from this area, you're going to see that there is also some pretty good source rock down here in the Sleipner and Huygens formations. This source rock is terrigenous influence. It's older. It's sort of lower middle Jurassic, and it's going to make gas and gas condensate. And these are mixing in the South Viking Graben. Now, there's a related paper I'm going to refer to several times here, written by Richard Patience. He wrote this for mid-Norway, but basically this is the same Graben system. Where did all the coal gas go? Where did all this go? We'll come back to that question a little bit later. So this is SVG oil, this is SVG gas, and there now is our cluster diagram. We have two subfamilies. Here's our similarity line. We've got the ones that look like dropney. We're going to call those dropney oils, aren't we? If we just use standard traditional hierarchical cluster analysis. Hierarchical cluster analysis really is designed, it's best applied to oil families where each family has one source rock for the origin of that oil. When you start getting mixtures, things get more complex, and that's why this is becoming misleading. You see the end member here is the Coley end member. Okay, so let's look at a complex table here. You see I've blown up now that cluster. I've gone and I've taken this cluster and I've blown it up. This one now that's the end member is not going to show because it's got such a big cluster distance, but I've just blown up this relatively tight cluster here, and we're going to look at it in more detail. You can see we could draw another similarity line right here, and that is going to split it into some sort of subfamilies. And let's look at some of these subfamilies here. Here's the green subfamily. You can see in the green subfamily, we have the dropney contribution ranges from 65 to 100%. Remember, this is a mathematical mixture. So up to 35% Sleipner-Huygens input here. Okay, and you notice there's an associated gas liquid ratio for each of these mixes. We could calculate that easily. Here then is this sort of white group right here. And here the range for the South Viking Graben contribution, the oil contribution, the dropney, is from 25 to 60%. And look at this red group right here, pink group, exemplified by PXM. This is 80 to 95% Sleipner-Huygens input, but at the scale of the previous dendrogram, we're going to call that dropney oil. So it's dominated by actually Sleipner-Huygens gas condensate input, and we don't see it. Where did all the coal gas go? Well, it's there, but we're not seeing it because of the analysis that we do. This is truth here. This is the mathematical mixture. This is a mixture of 10% dropney with 90% Sleipner-Huygens. Now let's compare the results we get by deconvoluting these mixtures. And I remember I said I was going to do it several ways. Let's use ratios. And this is the way many publications have done allocation or deconvolution of mixtures. We're just going to use the ratios, those 17 ratios. And this is the result we get if we do ALS, alternate least squares, of those ratios. And you can see here we have a tremendous error in the calculation of the amount of the Sleipner-Huygens contribution. That's an 80, that's an 80-something, 82% error. So that's a problem. Look at the predicted GLR here for this mixture right here. The gas-liquid ratio is 11,500. But if we use alternate least squares of ratios, we're going to predict 8% of the SVG gas. Well, that's somewhere up here between these two. That's a prediction of a gas-liquid ratio of about 2,000. So you might go to your management and say, well, we predict that when we drill these prospects, we're going to have a GLR of about 2,000. We're going to have a nice black oil, when in fact, this hidden SVG Sleipner-Huygens input is going to give you a much higher GLR when you actually make your production. We can also do alternate least squares on concentrations, and I've done it two ways here. We're dealing with dead oil here. So what you can do is you can reconstruct the whole liquid. So that's now C6 plus, and I'm not going to go into the details of the mass balance, but you can go to the geochemical database, you can go to the GOR of the field, and you can recalculate what the C6 plus distribution is. And here you come a little bit closer to the actual Sleipner-Huygens input, 75%, but you're still off. You're still, wrong, basically. However, if you reconstruct all the mass balance from C1 plus, and again, you can do this from the data that's available in the database, for example, the GeoMark database, and you've got a GOR from the field, you can reconstruct and do your mass balance. You get an exact answer. This is the same as the original mathematical mix. So I guess what this is saying is, don't use ratios to deconvolute these kinds of mixtures. Use alternate least squares of concentrations and do that based on the whole fluid. So your ppm calculations are going to change as you go from whole liquid to whole fluid. You have to do a mass balance, and that's pretty simple to do, and you can get the correct answer. So I'm going to show now in a figure basically what I've just shown you in this table. Here we have the mathematical mass percent of the Sleipner-Huygens gassy source. And the mathematical mixture is right along this solid line, okay? This is the ALS mass percent. You notice if you use C15 compound ratios, the ratios don't mix as a straight line, they mix as a curve. And in fact, you don't even see that gassy contribution until you have more than 90% SVG gas, more than 90% Sleipner-Huygens. So where did all the gas go? Where did all the coal gas go? It's there. But if you use ratios, you won't even see it. If you normalize to the whole liquid, that is C6 plus, and don't account for the gases, you come a little closer, but it's still an incorrect answer. If you do C1 plus mass balance and calculate the mass percent of SVG gas, you get the correct answer. It's right along this whole fluid line, which is also the mathematical mix. So we also see this with the isotopes. This is the same family, and we've calculated the GLR and the gas-liquid ratio. Where did all the coal gas go? Well, here is the isotope composition of the Dropney oil, right here. And you can see that that isotope composition is a little more negative than -30. And it doesn't really change very much as you add more and more Sleipner-Huygens gas condensate. You can get up to about 80% Sleipner-Huygens gassy input, and your isotope value is only changed by maybe about 1 per mil, 1 per mil. You're not going to see that until you have really high concentrations of that SVG gas. So this is also, the isotopes are also biased against the high GLR end member. They're biased for that low GLR, that oily end member. And this also means that your prediction of the gas liquid ratio is going to be anomalously low because there's a tremendous contribution from the gassy end member. Okay. Now, in all fairness to Patience, his comments were made about mid-Norway here. Remember, he said, where did all the coal gas go? Well, yeah, they're different basins. This is a little bit different basin up here in mid-Norway, but we're basically dealing with the same rift and that same bias against the coal gas. So for family 2 here, we have the oily end member, the gassy end member, and that's the South Viking Graben down here. And those are the end members that we mix mathematically. And, you know, we've got Dropney and Huygen, and there's the stratigraphy. And here in the central Graben and north and central Graben, we have the same sort of situation. The Dropney is equivalent to the Kimmeridge, Upper Jurassic, oily end member. The Pentland is the gassy end member here. It's the Huygen-Sleipner. And up in mid-Norway, it's really, they have different names, but it's really pretty much the same story. The Speck is the oily end member, and the Aura, which is a little bit older, is the gas condensate end member. So we do have the same bias against the coal gas contribution in these mixtures throughout the area. So here's our family 3, again, 5% increments on the mixtures, and all of the samples are plotting pretty close to each other here. Many of these are up to 95% of the gassy end member, which in this case is the Pentland Shale source rock. And these, this is the Kimmeridge clay source, which is, you know, equivalent to the Dropney basically in another part of the basin. And here is our bigger cluster distance with the outlier, which is the Coley end member. So all of these you would conclude from this hierarchical cluster analysis is, oh, these are Kimmeridge subfamilies. And the differences maybe are due to the slight differences in cluster distance, or maybe due to organofacies variations. And so we can go to the same sort of chart again and blow this up, except for the outlier, the end member, gassy end member. And you see the same sort of situation. Here is a fairly tight group where we've got 65 to 100% Kimmeridge oil. But down here, you know, we have 85 to 95% of Pentland gas. So our family GHK, our sample GHK here is a 10 to 90 mix. If we do alternate least squares of the ratio, we only get 10%. We're predicting an allocation of 10% from the Middle Jurassic Pentland. 10%, that's not a gas liquid ratio of 18,000. That's a gas liquid ratio of about 3,350. So we would not only classify this oil incorrectly from our cluster analysis, we would make incorrect predictions of physical properties, not just GLR, but other physical properties as well. And here's the corresponding chart. It's the same story. You know, you don't even see the gas condensate contribution until you get to really high allocation from that Pentland Coley source. Well, I went pretty fast through this, but I think the impact here is really an important thing for us as geochemists and geologists to be aware of. Mixtures that are rich in gas condensate tend to cluster with those dominated by the oily end member. Alternating least squares of compound ratios fails to accurately deconvolute these mixtures, but alternate least squares on a whole fluid basis gets you the precise allocation. HCA of compound ratios identifies genetic fluid families through a range of molecular weight. You need to specify that range, but it can be misleading for mixtures of end members with distinct compound concentrations or gas liquid ratios. Alternate least squares of ratios can deconvolute oil-oil mixtures. Yeah, that's because these guys have similar gas liquid ratios, similar concentrations of components, but mixtures having different GLRs, compound ratios, and concentrations mix in a non-linear fashion. So we're going to use concentrations to deconvolute those mixtures. Those are also ratios, Concentration is also a ratio, but in every case, the denominator is the same, parts per million, right? The denominator is always the same. So they mix linearly. ALSR fails to deconvolute mixtures of oil and gas condensate. It underestimates the GLR and other physical properties. I didn't show others, but it'll underestimate GLR. And it underestimates the contribution from the gas condensate. Where did all the coal gas go? It's there, but you're maybe using the wrong technique to try to deconvolute that mixture. ALSC deconvolutes mixtures. By the way, I just showed you examples of binary mixtures, but you can do ALS, alternate least squares regression, on more than 2 end members. But quantification requires internal standards. Some labs don't co-inject internal standards with the samples. They can't give you anything but a ratio. They can't give you concentration. ALSC of whole fluid, C1+, where you do a mass balance, is more accurate than ALSC of the whole liquid. Many interpreters use ALSR to deconvolute mixtures, thus yielding inaccurate results. You can go to the literature, and there are literally dozens of such papers. And I've had discussions with some of the people involved. They're some of my friends, and they say, well, you know, we're confident in this approach. It gives us very reproducible results. And I would show them this diagram right here, this little figure. They're right here, okay? There's a difference between precision and accuracy, and I think we want to be over here. We want an accurate result. So here are a collection of sort of references, and you know, this is the old way of doing it, where we mixed the end members in the laboratory. You don't need to do that anymore. It's tedious, time consuming, and alternate least squares works just fine. Here's a paper. This is our in-press paper in APG Bulletin. And here is the reference to the talk, which is recorded in the APG meeting that just occurred. Okay, so I hope I didn't take too much time there, and I'm looking forward to any questions you might have. Thanks a lot.
Thanks, Ken. Any questions? I haven't seen any come through the chat window or from our tiny URL, but we do have a number of our colleagues in Norway still on the line. So before I jump in with a question, which I do have, I'm wondering if any of our colleagues from Norway would like to jump in. Okay, so Ken, my question for you then is, so for our colleagues over there who are, you know, actively exploring offshore, could you give us a 1 or 2 sentence sort of practical application of your talk to production, to oil exploration and then production?
Sure. You know, the example I gave in the talk was prediction of gas-liquid ratio. And, you know, you can predict that gas-liquid ratio accurately if you do the deconvolution of the mixtures correctly. And that's very important when the management comes to you and says, well, we can drill this well if the GLR is below some value. If it's a black oil, if the GLR is less than 3,000 standard cubic feet per barrel, we can drill this well. But if it's higher than that, we aren't interested in a gas producing well. We aren't interested in gas condensate. We're interested in black oil. That may be their specification. And you use ratios to predict then the GLR. You will underpredict the actual GLR that you get. And it can be a tremendous, the examples I gave, you know, you're going from black oil to predicting black oil to actually seeing a really light gas condensate. And there are different parts of the world where this is a severe problem, at least as severe as in the North Sea. For example, Northwest Shelf of Australia. You're mixing Triassic with a Permian, a gassy source, and a Triassic oily source. And the difference in GLR there is sometimes 50,000 GLR for the gassy source. So it's it is an insidious problem, and it's something that we need to recognize and handle if we want to make predictions in terms of exploration, right?
Yep, that's great. The other thing that came to mind, and then we'll just wrap up, is that in Alaska, you get taxed differently according to which lightness of oil you produce. So that kind of prediction may be helpful too because of the
Yeah.
tax structure.
Yeah.
So,
The thing that's
okay.
kind of astonishing to me, and I've been doing geochemistry for more than 42 years now, is that, you know, throughout the world, there are a lot more mixtures of oils and mixtures of oils and condensates than would appear to be at first glance. Different places, you know, Brazil, Venezuela, the North Sea, you know, west coast of Australia, Saudi Arabia. You've got this deep source, Silurian source, and then you've got the Hanifa Hadria Jurassic source above the salt. Yeah, they mix, and that's going to have a tremendous effect on the composition, and your ability to allocate that is really important for predicting physical properties.
Yep. Allocation, as you know, is becoming more and more important in our field. I'm going to talk about, so Ken, here's a question for you, if people will just hang on a little bit longer, because this is something I'm going to talk about tomorrow. Ken, we are fighting over bubble and dew point curves. Do you have an opinion about how well we know the PT of phase transitions?
Well,
The holy grail.
yeah, that's a tough one, and the best work that I've seen is sort of empirical, and this is some work that was recently, I don't know if it's published yet, but it's been shown by Andrew Murray and
and Jiang.
Zihong.
Yeah.
What's his last name? I forgot his last name.
Jiang He, the founder of ZetaWare.
Yeah,
he's the one I've heard speak the most. Yeah, sorry.
Yeah, they basically have constructed a diagram, but again, there's some slop in the diagram for prediction of the phases, and it's empirical. It's an empirical model. So I would kind of defer to them. I would defer to them to answer that question. I could show you the diagram. I've used it, and it's sort of a V-shaped diagram that predicts the phases that you will encounter and the bubble point and dew point.
Right, and so in this same questioner asks that they also, I guess people that he works with also point to a lot of certainty regarding this fight over bubble and dew point curves. So I would say that we actually brought in Jiang He right after the BPSM meeting last year. We had a 3-day science training, and this was the most intense and also I should say thorough explanation of phase that we ever had in the Stanford BPSM program. It was eye-opening. And so if it's still being, as this speaker says, fought over at companies, that might be because they haven't seen it in that formal way. I don't know, but it was a total eye-opener for those of us who went to that 3-day training meeting last year. And I think with that, I'll copy all of these comments. I'd like to turn it over to Tapan to close out the meeting.
All right, so thank you everybody for joining us for the first half, the first day of our annual meeting. We have more talks for you tomorrow on carbonates, gas hydrates, and shales and others. So same time tomorrow and also same link. So please join us again, and thank you for joining us today. So that closes this session officially. Feel free to make arrangements if you want to chat with the students. Thank you again for your support.
Thanks, everyone. We'll see you tomorrow. Email me if you have questions.